Here's a fun little question about a car on a lift. The car weighs 1,300 kilograms. The lift weighs 200 kilograms. The car starts at rest at a height of 2.5 meters. And then the lift lets go. There's a spring that keeps the lift up with a spring constant of 500 newtons per meter. And there's some damping going to be on the lift, typically with a side cylinder of oil or something like that. And the goal of the damping is to keep the car from slamming down too quickly, because if it falls quickly, it'll also go down too low. And we want the car to go no lower than minus a half of a meter. And so we want the minimum to be a minus a half. That will be the lowest it goes. And so the equation is the mass, the combined mass of the car and the lift, times the second derivative of the displacement. This is mass times acceleration for people interested in physics. And this is plus the damping times x prime. You can think of this on the left-hand side as the force is minus the damping. And then 500, the spring constant, times the displacement. Again, you can think of this on the right-hand side. The force is against the spring. And so this is our equation. And we want to solve it with these initial conditions. And then find B so that the minimum is minus half a meter. It's a second order equation. It's linear in x, and it has constant coefficients. And so we're expecting an exponential solution of some sort. We're trying an exponential solution in this equation for the lift. And there are two possible values for the coefficient in the exponential. We'd like to take the least one, which corresponds to this square root, having an imaginary component, because b squared is less than 3 million. So that's our assumption here. And so we get a solution that's x equal to e to the minus b over 3000 t. And then for the part that involves the square root of minus 1, we have cosine of minus what's in here times t, and sine of the same term involving t. And so now we want to pick C1 and C2 to match the initial conditions, and again find the lowest point that x reaches with this oscillatory solution. So the first drop will actually be the biggest one. We're solving the initial conditions for this problem with the lift that has the car on it. The car starts at 2.5 meters. And that means that C1 in the solution is 2.5. And now to calculate the second initial condition, meaning that the car starts at rest, we need to calculate the derivative. So we have the exponential times the derivative of cosine, which gives us sine, times the constant in front of t, and then the derivative of sine, which gives us cosine, again times that same constant that's in front of t. And then when we differentiate the exponential, we get the exponential again times the derivative with respect to t of the exponent, which gives minus b over 3000, and then the original solution, 2.5, the c1 times cosine, and c2, which we haven't decided yet, times sine. So we want to set this equal to 0 because, again, the car starts at rest. And so when t is 0, the sine terms are both 0 because there's a t in here. And the cosine terms are both 1 because cosine of 0 is 1. And so the coefficients of the cosine terms have to be 0, which is saying that C2 times the quantity that's in front of t in the cosine and sine minus 2.5 times b over 3000 is equal to 0. That determines C2, which I'll write down in a minute. It also determines that in the actual solution, in the original solution, the cosine terms in x prime here, this coefficient of the cosine term here multiplied by that, and the coefficient of the cosine term times C2 over here, they cancel. So actually x prime of t does not involve a cosine term. X prime of t is in fact what we're looking at here, with only the sine terms multiplying the exponential with the appropriate coefficients. We have found that C2 is 2.5b divided by the square root of 3 million minus b squared. Again, b here is the damping. We would like to figure out what the minimal damping is that keeps the car from going more than half a meter below the base of the lift, well, the point that we're calling 0. And we have decided that the x prime is actually equal to this, where there's only a sine term times the exponential, and then the cosine term vanishes. And I've put all the coefficients here, minus 2.5, that was C1, times this factor, and then minus b over 3000 that came from differentiating the exponential, times C2, which is sitting over here. Notice that the minimum, the oscillation will go like this. The minimum is the car drops. It's the first time where the derivative is 0. So what we're actually wanting to figure out is the first time after the start in which the derivative is equal to 0. Notice that this thing over here is never 0, right? In fact, it's negative. This is negative, and here we have b squared times 2.5 over some square root, which we assumed is positive, and so this factor is negative. So the only way that x prime is 0 is for the sign to be 0, right? The exponential of any real number is never 0. So the only way that that happens is that the sign is 0, and the first time the sign is 0 is where this whole quantity is pi, right? The first t bigger than 0, for which this is 0, is when t is, this whole quantity being fed to the sign is equal to pi. So that tells us the first time. Let's look at that first time. Let's look at how far down x goes when x prime is 0 for the first time. We decided that the first time at which the height has a change in direction, so a minimum, is where the time t sub l, where this multiple of it is pi. And so if we plug that back in, we get e to the minus b over 3000 TL times this minus 2.5, because remember the sine of this is 0, and so we have the height equal to minus 2.5 e to the minus b, and then I plugged in what TL is in here, and that's what we have. And so we want that height, that first minimum, to be minus half a meter, and that gives us that the thing in the exponent is equal to minus 0.5 divided by minus 2.5, which is 1/5, and the log of 1/5 is minus the log of 5, and so we get plus this quantity is equal to the log of 5. This is actually a quadratic in B because we can multiply the square root through and square both sides, and then we have a b squared here, and we have 3 times 10 to the 6 minus b squared on the right hand side. So we can actually solve for b exactly, but we could of course always use some kind of approximation to figure out what b is to any accuracy that we want. We're finishing to find the damping. We have that pi times b over the square root is equal to log 5, squaring both sides, collecting the b squared terms, moving the coefficient of the minus b squared to the left hand side, and then solving for b. We have this expression exactly, and just to give ourselves some sense of that, this turned out to be 789.728 rounded to 3 decimal places, and that's the damping we need so that the car dips down to minus half a meter, and then there'll be some oscillation, but it will not dip down any further.